Assalamualaikum warahmatullahi wabarakatuh and a very good evening to Dr. Fadia, my SIM3029 lecturer for computational fluid dynamics. So today I will be presenting question number 3 for the final assessment for this course. So let's get straight into it. So for question number 3A, referring to any of your mathematical equations, expressions, or solutions in question 1, justify and conclude whether the model interprets, firstly, an ideal fluid or a real fluid. Okay, my answer for this is that the model describes a real fluid. Why? The x momentum equation includes the viscosity term, implying that the model represents a fluid with viscosity taken into account in the governing equation. When there is viscosity in the governing equation, it directly implies that it is describing a real fluid. On the other hand, if there is no viscosity, it is describing an ideal fluid. Next, Newtonian or non-Newtonian fluid. My answer is the model describes a non-Newtonian fluid as there are non-linear terms such as the second derivatives of the spatial coordinates, the second derivatives in the x momentum equation. For the third question, a compressible or an incompressible flow. The model describes an incompressible flow. Why? Okay, let's see. Let's use the given continuity equation, nabla.u equals to 0, right? Okay, now let's take the Lagrangian derivative equation, del rho over del t plus rho nabla.u equals to 0. Since we have nabla.u equals to 0, to make the whole equation true, we need to set the delta rho over delta t equals to 0. When delta rho over delta t equals to 0, this means that density is constant throughout the flow. Thus, the fluid represented is incompressible. Next, steady or an unsteady flow. The model describes a steady flow as it does not change with time. What I mean does not change with time, any variables in the flow does not change with time. There is no terms containing the time derivative within the governing equation. Last but not least, for question A, laminar or turbulent flow. The model describes laminar flow as there are no Reynolds average turbulent terms in the governing equation, such as omega and so on. Moving on to question B, using the principles of dimensional analysis, dimensional parameters, and similitude in hydrodynamics, explain how the transform ODE can be acceptable to approximate the solution of the original PDE. So let's look at from two different angles. Using the principle of dimensional analysis and dimensional parameters, first, it tells us that complicated physical problems often depend on smaller number of independent non-dimensional groups rather than many dimensional variables. In the original PDE, there are many variables including x, y, and so on. However, after non-dimensionalizing it and using similarity reduction, the system only depends on dimensionless groups. Additionally, since the original nonlinear PDE contains only two independent variables, x and y, it can be more complex to solve directly as the solution depends on both spatial directions. So by introducing similarity variables, the original PDE can be reduced to a single variable ODE, which uses the variable eta. Next, let's look at it from the principle of similitude. The principle states that the two flows are dynamically similar when they have the same dimensionless governing equations and the same dimensionless parameters. In question 1D, after non-dimensionalizing the whole system, the transformed ODE depends on parameters R, K, and M, which are the given parameters in the question, which depends on the matrix number. Even if the two real physical systems have different values of A, B, C, D, and so on, they will behave similarly as long as R, K, and M are the same. Okay, so this means the dimensionless velocity profile obtained from the ODE can be used to represent the original PDE, but in a scaled way, so a less complex way in order to solve it. Okay. Last but not least, let's move on to question C. Discuss your solutions in question 2 in terms of stability and physical interpretations and implications to the real problem. Okay. First of all, let's discuss the stability of the solution and its physical interpretation. In question 2, we solved the hyperbolic PDE using a finite difference method, FDM, with a rectangular grid and a central difference approximation. The FDM was applied where the unknown interior points are solved simultaneously using a matrix equation. Okay, since the new time level values are obtained by solving a system of equations, this is an implicit method. So as we know, implicit methods are generally more stable compared to explicit methods, especially for larger step sizes. However, numerical behavior still of the solutions still depends on the chosen grid sizes. So in this case, we were given H, which is the step size for X in the X direction as 1/5, and K, which is the step size in the direction of T, as 1/2. So if the step sizes are too large, the solution may still show like numerical oscillations and reduced accuracy compared to the real physical behavior. So choosing the step sizes are very important for the stability of the solutions. Last but not least, let's move on to the implication of the real problem. Okay. For question 2, in the real shallow coastal region, the solution represents how a velocity disturbance propagates and reflects due to fixed boundaries. So as the boundaries given in the question, the results suggest stronger disturbance in the interior compared to the points at the boundaries, which indicates wave propagation and reflection effects. If the grid spacing is too large, numerical errors may distort the wave amplitude and shape. So, as I said, careful choice of step sizes, in this case, step sizes for X and T, is really needed for realistic prediction. So I think that is all for my presentation of question 3 for my FA. Thank you so much.